All right, hello everyone, and today we'll be talking about Riemann sums and what the integral actually is. Now, as I have right here, the integral is the as simplest you can put it, the area under a curve. And this right here, what I have right here, is a definition of an integral, right? Because all an integral is, and we'll explain how integrals work here, is that we have this limit, right? And this is where n approaches infinity. This is basically stating, this entire thing right here is all stating that as we start to approach an infinite amount of small rectangles under the area, which what n represents, the number of the rectangles, this represents the width, or one represents width and this represents width and this represents the length, right? This is the top and bottom of the rectangle, from bottom to top of the rectangles, and this right here is just the that width of that rectangle, right? And as we infinitely approach these values, we end up with the integral, and we'll demonstrate it. Now we move on to Riemann sums, right? So let me get a little graph going. All right. Very bare bones graph. All right. Very bare bones graph that we have here. Let me copy it for later use. Or actually, let's have a few. And we're going to put them side by side because what I'm going to represent is a few Riemann sums. All right. Now, for all of them, for all of these, we're going to do x cubed because I feel like that's really simple. But basically, I'm just going to draw different types of Riemann sums. A Riemann sum is a way to approximate the area. And we approximate this area by doing the same thing, or what an integral should do. But basically, we take a bunch of small rectangles and we fit them under the area. Because, let's be honest, do we know how to figure out the area of a curve like this? We can fit triangles and trapezoids and everything like that. And we know the areas of trapezoids and triangles, right? 1/2 base times height, right? But this isn't a triangle. It's a curve. So, the alternative method, we draw small rectangles. So we're going to have these two as our little limits, our little bounds. These would act as our limits of integration, right? Now, for starters, we're going to draw 4 rectangles now. So let's split it in here, here, here. That's 3. That's 2.5. 3.5. And it same as follows for all of these graphs, correct? Yeah. So now we're going to start drawing the rectangles. As you can see here, only the left point of these rectangles touches the graph. This is what we call a left endpoint Riemann sum. Because the left end touches the graph, right? And as you can see, we have this little area for each of them right here. And I know I'm not a good artist, but this is an underestimate of what the area should be, right? Because we're missing these little sections. There's another method, though, which I will show now. And as you are starting to see, this is a overestimate, correct? And this is what we call a right endpoint. Right endpoint. Now these are pretty bad ways to estimate, wouldn't you say? We can get even closer to estimation. And we can do this by making a midpoint. And as it suggests, the middle point of the rectangle touches the graph. And I'll show you how this will work. Basically, you bisect all, so the sections that you made, you bisect it even further, and then you draw these rectangles. And as you can see, you have a little bit of overestimation and a little bit of underestimation. And it kind of just balances out as such. And this will get you a really good approximation. And it's a midpoint. Now, there's another approximation method with Riemann sums, and this is having to deal with, hold on, let me move this over here. And it's to deal with another kind of shape that we know the area of, and this is trapezoids. Now, for this, I'm going to draw a sine curve, actually. Something like that. All right. Now, for this, we can actually fit a bunch of these little trapezoids in here. And as you start to see, they're working. And then, yeah. But we're going to stop. These are going to be our limits, and we'll call these in 2 pi, right? Now, for this, let's take one of these trapezoids out, right? Something like this, right? So for each trapezoid, the height will be considered this bit. That's what the height will be. And this can either be base 1 or base 2, depends, but we'll call it base 2, and we'll call this base 1, right? And basically, the area of a trapezoid is equal to height over 2, and then base 1 plus base 2. And that's the area for a trapezoid. Very simple stuff. You can try them out, right, by plugging in the lengths and widths. And all you have to do is just take the function, right? If we want to get this endpoint, we take the function at that number, we plug that number into the function, and we'll get a value. And we use that value for any of these points. It applies to any of these. And for this one, we just have to use these lengths. So we have to use both values on both sides. We have to use 0 and this value. And that's how we find those bases, right? And to further iterate on this point, let's take a look again at the integral, right? An integral is set up like this. You'll have a function and then dx. Now, this little dx right here stands for a differential piece of a function, right? This little dx actually stands for this little small piece of whatever kind of sum it is, but it's going to be, for integrals, it's rectangles. It's an infinitely small piece. This acts as the width in some cases, and because you're multiplying by the function, right, which is the points of these, like any point of those functions, you're basically multiplying the length and width. And that's pretty much it. And then that's almost how an integral works. But time to take it a further step. And I'm going to show you, for those who aren't physics, are probably going to understand this better. Or I can just paste a graph. Correct. Okay. Crap. This is on me. Hold on. All right. We're going to do 3 graphs separately again to further demonstrate this. All right. Now, instead, we're going to make these because, and for those in calculus should know this, but let's make this a position versus time graph. This is a velocity versus time graph. And this is an acceleration versus time graph. Now, for those of you of physics, you know that the position graphs usually look like this, right? And then the velocity graph will look something a little like this, and then the acceleration graph will look something like this. Very simple stuff. Okay. So if, let's say, we wanted to find the area of the acceleration graph, right? From 0 to a later time, which we don't know, right? We want to find all this out. Fortunately for you, if we integrate that function, right, and we set the same bounds, right, but this time we're not taking the area, we're taking this point and this point, right, it will turn out that this area right here is equivalent to this point, the v of t of f minus or 0, which is 0. And in total, you get the area of this other curve. And that's how that works. And to further demonstrate this, so let's say we wanted to find out the area of this, right, from here to here, the same time bound. If we were to go to find that same point at that same given time, it would return to us the area. And this is a velocity graph. And for those of you in physics, you know that the area of a velocity graph is the change in position, is like that, right? Or hold on, I miswrote it. Area of a velocity versus time graph. But this graph basically shows change in x, if you can see, because at this point we have displaced let's do another variable, a y amount. Over here we've displaced a 2y amount, you know? And really, this area, and you can try this out with any function, right? If you know its integral, you could try something like x squared, not even x squared. You can try it with something y equals x, and then the integral of y equals x is actually 1/2 x to the 2, right? That's the integral. Just put them in Desmos, and if you want to take the integral from this to certain points, plug in your bounds into this function, and you'll find out that they're the same thing. And it's a really cool thing to see in graphs. And that's pretty much it. That's pretty much all there is on Riemann sums. It's basically that whole idea of finding a geometric shape that you know the area of and fitting it under that curve. And that's how integrals work. And there's so many other properties in that, but this is just basic Riemann sums. And yeah, I hope you have a great day, guys. Peace out.